So it's a great honor to give this overview of the future of particle physics in Japan. So I just wanted to start by saying that there is a long tradition of particle physics in Japan. 120 years ago, Nagaoka proposed the Saturnian model of atom, which was cited in Rutherford's historical paper. Nishina was a founder of experimental nuclear and particle physics, building accelerator and making important discovery before the World War II. Japan has a long tradition of theoretical particle physics. Yukawa, Tomonaga, Nambu received a Nobel Prize. But for the last half century, there have been significant contribution in experimental physics from Japan. So Kobayashi Masukawa theory was confirmed by the experiment at Bell at KK as well as Babar at SLAC. Koshiba's Kamiokande project detected the supernova neutrino, and the super Kamiokande discovered neutrino oscillations. So the question then I'd like to pose in my talk is, will Japan continue to make world-leading discoveries in particle physics in the 21st century? Okay, so there are actually many facilities in Japan. So three major areas are in Kamioka, which host Super Kamiokande, and they're building Hyper Kamiokande and Kamran. And KK hosts Bell 2 experiment and J-Park. And so there are many things happening. So to give some organization principle, I borrowed the example of US Department of Energy and organized my discussion into 4 areas: energy frontier, intensity frontier, cosmic frontier, and theoretical physics. So I'll start with intensity frontier. So there are many activities in Japan, starting with T2K. So T2K is a project which sent a neutrino from Tokai facility at J-Park to Kamioka facility. And it started in 2010. And by now, it has accumulated of order 10 to the 21 protons and 3 sigma exclusion of large area of this moduli space of CP violation. And CP conservation has been excluded in 90%. So this is one of the latest plot. This blue solid curve is 1 sigma for T2K, and red is a combination of with Super Kamiokande. So there is an upgrade plan. So for example, to increase the number of protons by order of 10, and it's already starting. And then so there are also upgrade both in beam power and detector. So so that's the next phase. And there is also corresponding upgrade in Super Kamiokande and building of Hyper Kamiokande, which I'm going to discuss next. So Kamioka is located here in Japan. And one of the important development is Super Kamiokande gadolinium project, which is to add gadolinium to Super Kamiokande to enhance neutron tagging efficiency. So this is a diagram to explain it. In fact, I was a director of Cabri IPMU when this was happening, and I was very impressed with the systematic and methodical way that this gadolinium addition was taking place. And so there are actually experiments is happening, and there are several exciting physics targets, including the detection of diffuse supernova neutrino background in the universe, and improving pointing accuracy of supernova, early warning of nearby supernova, and enhanced new discrimination of atmospheric neutrino, and reduced background for proton decay detection. So this is the timeline started with Super Kamiokande in 1996, and then it has gone through several phases, and gadolinium loading project. So basically for the last almost 20 years, 15 or so years, there have been some prototype experiments to make sure gadolinium loading works, and the loading actually started in this last phase. And so this is basically, this diagram shows the progress in this. And so if you go to Kamioka facility, it's like a city underground. So there are many experiments, and the Kamran and its upgrade Kamran Zen is another exciting experiment at Kamioka. And so Super Kamiokande is a water Cherenkov detector, but the Kamran is a liquid scintillator. And the aim of this new target is neutrino-less double beta decay experiment, understanding the nature of neutrino mass and low energy neutrino astronomy. And also there are interesting geophysical experiments. And so this Kamran has been led by RCNS at Tohoku University. But recently, Tohoku University and Osaka University joined forces to form a new laboratory for super clean facility in cavity near Kamran, and it's called Kernel. And they are actually soliciting users from the community. So if you are interested, please contact them. Hyper-Kamiokande construction is going on schedule, and it is very exciting. And this is expected to establish CP violation in excellent statistics and large region of CP violation parameter space. And also expected to be able to tell the difference between normal and inverted neutrino mass hierarchies. And extends the range of supernova explosion, neutrino from supernova explosion to megaparsec. And if that happens in our galaxy, then I'm told that they can detect 50,000 neutrino. And another interesting, exciting possibility is that, well, because of this high order of magnitude improvement of sensitivity for proton lifetime, it covered most of the GAT models. So Super Kamiokande excluded minimum SU5 GAT, but for example, Hyper Kamiokande covered most of supersymmetric SO10 grand unification. And this is a more relatively recent photograph where the excavation has almost completed. And now I understand they are starting to construct a tank. And so I'm told that the operation will start in 2 years. So that's really exciting. So this is the aerial photo of KK. We see the Mount Tsukuba over here. And one of the exciting experiments of doing over there is upgrade of Bell 2 at KKB accelerator. And the previous version confirmed the Kobayashi Masukawa theory. This is a beautiful unitarity triangle to confirm the model. Bell 2 at Super KKB aims to discover physics beyond the standard model of particle physics. So this is the diagram of Super KKB, and this is a diagram for Bell 2 experiment, and there are a few specifications written over here. So Super KKB has achieved the world record in luminosity, and Bell 2 has already taken 575 inverse band and reached about half of already the previous Bell experiment. And they are targeting CP violation, lepton flavor violation, and rare event. And they plan to increase the luminosity further. So currently it's 34, but further to one more order of magnitude, and also upgrade Bell experiment. So JPERC is also managed by KK, I understand, and it's on the ocean over here. And so what it does is that one of the things is that it has a very high power proton beam. So that's very important for intensity frontier. And so one of the things that they are doing is to measure G-2 electric dipole moment, please excuse me, or muon. And in fact, they have done first ever demonstration of acceleration of positive muon by RF cavity at 100 kV, keV. And so this is the diagram from the last year. And so my understanding is that this is the only experiment that can test this interesting result of cellular VML. So since you have lots of particles, so you can do search for a rare event. So the COTO is one of the experiments which searched for KL into pi nu bar. And so this is a CP violation rare process. And so the original COTO experiment was to search this process. And as of 2021, no event has been observed, but they have increased the sensitivity, and they are now over here. And so COTO2 actually increased this sensitivity by order 3. And so they are actually aiming at not only searching for it, but actually measuring it. And they are aiming to run it in 2030. And there are also a couple of exciting opportunities for charged lepton flavor violation detection. So COMET is an experiment to search for mu-E conversion. So the current upper limit is like this, and they are aiming at actually improving that the order 2 or even 5 in the next phase. And in the first phase, the construction of first phase is already in progress. And well, they are aiming at actually starting next year. And so these are current photographs of the construction of these facilities. Okay, so this is again, this is charged lepton flavor violation search. And this one is mu plus going to E plus and gamma. And this experiment, MEG2 muon electron gamma experiment, is actually taking place in German Paul Scherrer Institute, but it was actually proposed and led by Toshinori Mori at the University of Tokyo. And one of the interesting features of this project is actually it's a DC muon beam as opposed to the pulse beam. So there are many complementary aspects of this experiment. And so there are lots of interesting possibilities to explore beyond the standard model particle physics with these at this intensity frontier. So let me move on to the cosmic frontier. And there are neutrino astrophysics, CMB polarization detection, and so I mentioned a few other experiments. But I have already mentioned the opportunity in neutrino astronomy in Kamioka. So I'm not going to repeat that. I just want to mention that in Kamioka, there are lots of opportunities in cosmic frontiers. And the CMB experiment is very interesting. In fact, Japan started pretty early. So there was actually a sounding rocket experiment led by Nagoya University in collaboration with UC Berkeley, and it was launched in Kagoshima. And but it was this activity was dormant for a couple of decades after this. But then Japan re-entered the scene at the beginning of this century, starting with a quiet project. And then in Polar Bear, Japan led receiver upgrade and made significant contribution in Polar Bear and the Simon's array. And so with this, there emerged the idea of actually launching a satellite project. But in order to actually demonstrate this satellite project on ground-based experiment, started with what's called ground bird. It's in Canary Island. And this is a Japan-oriented project. But it was meant to be the demonstration, but it also has very interesting physics component, in particular measuring the optical depth of ionization, measuring from the ground. And then in Simon's observatory experiment, which is starting now, Japanese team has contributed through the entire path of CMB photons. So I have some diagram to show that in the next page. So this is the Japanese contribution. So starting from 4-buffer and grid calibrator, and then Japan has contributed significantly to these half-wave plate technologies, and then cryogenic as well. So through the entire CMB photon path, Japanese team has made important contribution. And in fact, one of the members of the executive board is Kusaka at the University of Tokyo. And so there is a possibility that the CMBS4 might be moved to Chile. But if that happens, I'm told that the half-wave plate technology that Japan has developed will become more important. So there is an opportunity for Japanese team to make important contribution to this project too. But so as you see that the Japanese team has been developing expertise and a team for the last couple of decades. And so I believe they are ready to go on to the satellite project, which is supposed to be launched in the next decade, led by JAXA and Kavli IPMU. And this is a very exciting project to test most of inflation single field solar models, and also determine the sum of neutrino mass. So this is a diagram to show the possibility. And as a theoretical physicist, I have some prejudice about the sum of the neutrino mass. So this is actually personally of interest to me. This diagram is actually about constraints that this can put on inflation models. So this is also a very exciting opportunity. The hyperspring cam and the PFS at Subaru telescope. So this is actually the Subaru telescope at the top of Mauna Kea in Hawaii that operated by Japan. And so the first one that Discovery IPMU contributed is a hypersupreme cam. And the operation has already completed, but still analyzing the data, and this release are expected later this year or next year. That's going to be the final data release of hypersupreme cam. And TFS, the prime focus spectrograph. So this will be a spectrograph. And the scientific collaboration actually started, or is going to start. Hitoshi Murayama is here, so he should be able to tell. But this month. So this is very exciting. And this PFS cosmology is in some sense complementary to DAISY. And so it will be very interesting. And this is primarily astrophysics experiment, but is of high interest in high energy physics as well. So Japanese team is also contributing significantly to IceCube project in South Pole, especially in data analysis, where the group at Chiba University played a very important role in identifying the first extremely high energy cosmic neutrino at the level of peta-electron volt, I believe that's how I should be read it. And I'll reveal the glacial resonance candidate, etc. And there are opportunity for multi-messenger experiment using this facility. But the Japanese team are also contributing, it's also contributing to the hardware development and productions as shown over here. So, energy frontier. So currently, there is no facility at the energy frontier in Japan. So, but Japanese team is making important contribution to Atlas experiment. And so, for example, contributed to the Higgs field in variety of ways: observation, property measurement, and search for self-coupling. And coming up with a new idea for new searches, and contributing stable operation of Atlas experiment, and also contributing a component for high luminosity LHC, and participating in the phase 2 upgrade. So Japanese team has been making a variety of contribution to Atlas experiment at CERN, but also there is this very important role that Japanese team is making in phasor experiment at CERN. So this is an interesting idea that so if you have a detector like Atlas, it's hard to measure forward jet because the beam pipeline has to go through it. So they had this idea that, well, if you actually extract the tangential direction to the circular LHC ring, and then place a detector about 480 meters from there, then you can actually measure the forward jet. And that there comes a new particle or neutrino. In fact, there is 100-meter block, so you can find some weakly coupled particles. So there is a possibility to search for new weakly interacting light particles. And they have already measured the neutrino at the highest human-made energies. And Japanese team is contributing both at the level at the beginning of the technical proposal to the development of variety of part of detectors, silicon detector and immersion detectors, and the analysis and plan for the next generation. And they are playing leading role. For example, the Tomoko Ariger is a phase new project leader, and Hidetoshi Otono, is a tracker project leader. So International Linear Collider is a very exciting opportunities for energy frontier in Japan. And its goal is precise measurement of Higgs coupling and Topcock properties and direct search for new particles at this energy frontier, and to also try to figure out where the next energy frontier would be. And the proposal is to have energy extendability of 250 GeV, and with possibly going to multi-TeV with polarized beams. So technical design report was already completed in 2010, and there have been a demonstration of technologies, and physics potential has been verified with full simulations, and etc. And to move forward, I think the idea is that this has proceed as a global project, and continue to fund for R&D. That's my understanding at the current status of International Linear Collider. And finally, since I'm a theoretical physicist, so I cannot I can stop telling you about theoretical particle physics, which is a part of high energy physics research. So theoretical physics include formal theory, which in archive we post a paper in HEPTH. So the definition of this area can be the study of theoretical structure and development of new theoretical tools in quantum field theory, quantum gravity, and string theory. And Japan has a long tradition of this, starting with Yukawa and Tomonaga. And the interface with mathematics is important and interesting because in this area, there are lots of new mathematics. And for example, in Kavli IPMU, we have important department both in mathematics and theoretical physics. Hiraku Nakajima is actually the president of International Mathematical Union, and Yuji Tachikawa is a young leader in formal theory. And there are also mathematicians who collaborate very closely with formal theorists, such as Ogata and Yamashita, and they have very productive collaboration with high-energy theorists. Interface with quantum information is also very exciting, and Tadashi Takayanagi is leading this effort in Japan as a whole. And there is a new direction of applying machine learning to use machine learning, but as well as understanding machine learning, and this is led by Koji Hashimoto. And phenomenology and model buildings are also very important and vibrant in Japan. So this is the application of theoretical insight to particle physics and cosmology, and the development of new experimental methods. So in particle physics area, there are active work in anomalies in B physics, and proposal for muon colliders, etc. And in cosmology, of course, dark matter search and gravitational wave physics. But there are also theoretical research to develop ideas for quantum precision experiment. For example, use of qubit and quantum entanglement as a sensor, and new type of bubble chambers, etc. And so this is another vibrant theoretical area. Japan has a very long tradition in lattice gauge theory, starting with the development of QCD PACS in 1986. And so there have been important contribution in calculating hadron spectrum and incorporating Lucia algorithm for quarks and estimating the finite volume effect. But RIKEN has a lot of powerful supercomputers. So this is a Fugaku exaflop computer. And these machines are used for first principle calculation of hadron interaction. So this actually is a diagram taken from Nature paper of Alice collaboration. So they actually use their first principle calculation of hadron interaction to compare the hadron correlation function with experimental data. And this shows that the incorporation of this first principle calculation of hadron interaction fit very well with the experimental result. And there are also significant activity in collaboration with Brookhaven Laboratory. There is a long-standing collaboration between RIKEN and BNL, which include actually the calculation of muon G-2. And KK also has an important team in lattice gauge theory. So there is actually significant activity in lattice gauge theory. So I posed this question at the beginning of my talk: will Japan continue to make world-leading discoveries in particle physics in the 21st century? And I hope that we have seen that there have already been significant achievement in the first 2 decades of this century. And there are many promising directions for the coming decade, both in experiment and theory. So it's very exciting. I just wanted to thank everybody. I am actually a string theorist. So I have never worked on any of these experiments. So I have to rely on help and contribution from many of my friends in high energy physics experiment as well as theory. And in particular, the Japanese Association of High Energy Physicists, led by Nakaya, provided me lots of important materials and also advised me about this presentation. And Kajita and Nakahata and many other people actually checked this slide to make sure that my presentations are accurate reflection of current status of Japanese effort in this area. So thank you very much for this opportunity to make this presentation. It's a great honor, and I'll be very happy to take questions. Thank you very much.